Okay.
Dear students, as you know, nowadays due to the problem of coronavirus, all the institutes, colleges are closed and students are unable to come to the institutions to cover their syllabus. But Khalsa College is responsible for the study of their students, their syllabi, their examination. So we are giving you these lectures through video to cover your syllabus and to prepare for your final examinations. So in the series, yesterday I delivered you a lecture on connectedness in topology, that was part 1, and today I am continuing the lecture as part 2, the next few terms on connectedness. And even if you are unable to understand some of the problems, some of the theories, you are always welcome through WhatsApp, through calling, or through any media to ask your problems. So now I am going to start the theorems in the connectedness in the topology, which are in series continuing from yesterday. So the first term today is, let X top be a topological space and Y be a subset of X. Then Y is disconnected if and only if there exist non-empty sets G and H, both open or maybe both closed in X such that G intersection Y is fine, H intersection Y is not fine, Y is a subset of G union H, and G intersection H is a subset of complement of Y. Here, what is given to us that X is a topological space and Y is a subset of X. We consider the relative topology Y tau. Here, since it is a relative topology, or you can say the subspace topology, all the members of tau Y, they will be constructed through tau by intersection with the Y. Suppose G is an open set in tau, then G intersection Y will be a member of tau Y. That means open sets in tau Y will be Y intersected with some open set in tau. Similarly, closed sets in tau Y are closed sets in tau intersected with Y. Here, we have to show that if Y is disconnected, then there exist non-empty sets G and H satisfying these conditions. Now, I start the theorem. Here, Y is disconnected. We consider Y tau Y as disconnected space. Yesterday we saw that if some topological space is disconnected, then always there exist open sets, suppose P and Q in X, such that their union is X, their intersection is phi, and the sets are separated. Here, since Y tau Y is disconnected, there exist open sets. P and Q in Y such that P is not Y, Q is not Y, and the condition will be that their union is Y and their intersection is phi. I repeat, these P and Q are the open sets in Y. But we know it is the relative topology, so open sets in Y means some open set in X intersected with Y. That means P can be expressed as G intersection with Y, where G is some open set in X. That means a member of tau. Similarly, Q is H intersection Y, where H is some member of tau, open in X. Now, taking these values of P and Q in these two relations, P union Q is Y, means G intersection with Y union H intersection with Y is equal to Y. Now, applying distributive properties of set theory, we can write G union H intersection with Y is equal to Y. Now intersection of two sets is equal to one of the sets. It is possible if the resultant set is the subset of the other set. That means Y must be a subset of G union H, which is one of the conditions we want. Here, Y is a subset of G union H. On the same way, we are also given that P intersection Q is phi. Substituting the values of P and Q here as G intersection Y and H intersection Y, we will get G intersection Y intersection with H intersection Y is phi, which means G intersection H intersection with Y is phi. Now intersection of these two sets is phi. We know that if intersection of two sets is phi, then each one of them is a subset of complement of the other. So what we will get here is that G intersection Y H is a subset of complement of Y, which is the second condition to be proved. So hence it is the proof of the first theorem here what we discussed today. Now I move on to the second theorem. The second theorem, the statement is a topological space X is connected if and only if every non-empty proper subset of X has non-empty frontier. So how we will prove it? The proof is again very easy. Just we have to keep in our mind some basic concepts related to topology regarding frontier, regarding closure, regarding interior. Here, since the statements contains if and only, we will have to prove both sides. That means once we will take topological space X to be connected, and we will prove that every non-empty proper subset of X has non-empty frontier. Conversely, we will suppose that every non-empty proper subset of X has non-empty frontier, and we will prove that the topological space X is connected. So first we have direct proof. Let X tau be connected. We suppose that the space is connected, and now we have to show that every non-empty proper subset of X has non-empty frontier. We will prove this by the way of contradiction. Suppose, if possible, there exists a non-empty set A such that frontier of A is phi. We suppose that there is a set whose frontier is empty. We want to prove that every non-empty proper subset of X has non-empty frontier, and we have supposed that some set A which is non-empty has frontier A is to be phi. Now look at what about A? A is A interior union frontier of A. What about A bar closure of A? It is A union frontier of A. Now frontier of A is phi. So A is equal to A interior union empty set. This implies A is equal to A interior. Similarly, in the second one, frontier of A is again phi. So A bar is equal to A union empty set, means A bar is equal to A. Now A is equal to A interior implies that A is an open set. So this means A is an open set. On the other side, A bar is equal to A. Now A bar is equal to A means A is a closed set. This implies A is a closed set. That means A is open as well as closed. A is a non-empty set. We have already taken here. Now what happens in the space X top? We are having a non-empty proper set A non-empty subset of X has non-empty frontier. Now this is given to us, and what we want to prove now, we want to prove that X is connected. Once again, we will prove this theorem by the method of contradiction. Suppose if possible, X is disconnected. Now, if X is disconnected, by the previous results, we know that there exists a non-empty proper subset A of X, which is open as well as closed. Which is open as well as closed. Now, A is open. A is open means A interior is equal to A. Also, A is closed. A is closed. Now, A is closed means A bar is equal to A. Now look at what the frontier of A is. Frontier of A is A bar minus A interior. If we delete A interior from A bar, we get frontier of A. Here, A bar is equal to A. A interior is also equal to A, and A minus A is empty. So frontier of A is empty. That means we have a non-empty proper subset of X which has empty frontier, which is again contradiction to the given hypothesis that every non-empty subset of X has non-empty frontier. So we arrive at a contradiction, and this contradiction is because our supposition is wrong. What we have supposed that X is disconnected, therefore it must be connected. So now we move on to the next theorem. In the next theorem, we are given that X top is disconnected and tau dash is a topology finer than tau. Now, the statement is X tau is disconnected and tau dash is finer than tau. What we have to prove that X tau dash is also disconnected. We are given that X tau is disconnected. Now look at X tau is disconnected. Again by the previous result, therefore there exists a non-empty proper subset of X which is open as well as closed. As well as closed. Now A is open. A is open means A belongs to tau. A belongs to tau, and tau dash is a final topology. That means tau is a subset of tau dash. A is a member of tau, and tau is a subset of tau dash, which clearly implies that A belongs to tau dash. That means A is open in the topological space X tau dash. Again, our A is closed. A is closed in tau. A is closed in tau. This means A complement is open in tau. And open sets always belong to the topology. So that means A complement belongs to tau. Now A complements belongs to tau, and tau is subset of tau dash. Once again, A complement belongs to tau dash. A complement belongs to tau dash means A complement is open in tau dash. A complement is open in tau dash means A is closed in tau dash. Now A is a non-empty proper subset of X such that A is open in tau dash, A is closed in tau dash. That means A is open as well as closed in the topological space X tau dash. That means the topology tau dash is also disconnected, which we wanted And now the last theorem of today, and the statement here is on the left side of the board. You can see the statement in the bottom. It is given that X dot is a topological space and E is a connected subset of X, such that E is a subset of A union B, where A and B are separated sets. What we want to prove that either E is completely contained in A or E is completely contained in B. Now we start with X dot is a topological space. X dot is a topological space, and we are given that E is a connected subset of X. E is connected subset of X. Also, we are given that E is a subset of A union B. E is a subset of A union B, where A and B are separated. That means A bar intersection with B is phi. A intersection B bar is also phi. Both of these are empty sets. Note that E is a subset of A union B. That means their intersection. If one set is a subset of the other, then their intersection is always the smaller set, and the smaller set here is E. So it is equal to E. We can write it as E is equal to E intersection A union E intersection B. We can write it like this. Again, E is a subset of A union B. Earlier we have intersection. Now what about their union? So A union B, union with E, is equal to the bigger of the two. That means A union B. These are the basic results. In fact, this result will not be used in this theorem, but these are the two basic results, that a set is a subset of the other, then their intersection is the smaller set and their union is the bigger set. Here we will use only the first of these two results, that their intersection is equal to the smaller of the two sets. Now look at E intersection B bar is a subset of E bar intersection B bar as a previous result. Now intersecting both sides with E intersection A, what we get? E intersection A intersected with E intersection B bar is a subset of E intersection A intersection with E bar intersection B bar. On the right side, since all the signs are intersection, so these can commute and we can write it as E intersection with E bar intersection with A intersection with B bar. Now E intersection E bar, once again the intersection of two sets is equal to the smaller set, and smaller is here E intersected with. On the other way, here it is A intersection B bar, and A intersection B bar we already know that it is equal to phi, and intersection of any set with phi is phi, that means empty set. So what we get, that E intersection A intersection with E intersection B bar, that means this set, we have proved that this set is an empty set, is phi. Similarly, changing the role of A and B, we can prove that E intersection with A bar intersection with E intersection with B is also phi, which gives us that the two sets E intersection A and E intersection B, these two are the separated sets. So I am going to write it here. Once again, what we have obtained till now, that E intersection A and E intersection B are separated sets are separated sets. That means, also we know that E was earlier equal to E intersection A union E intersection with B. This result was already with us. What is the, if E intersection A and E intersection B both are non-empty sets? If these both are non-empty sets, then note that their union is E and the two sets are separated, which will make the set E as a disconnection, which will be a contradiction because we are given that E is connected. That means at least one of them should be empty. Either they should be empty or they should be empty. If the first set is empty, if E intersection A is 5, from the same result we can obtain E is equal to 5 union E intersection B. That means E is equal to E intersection B. And if intersection of two sets is one of the sets, then that set is the smaller set. That means E is contained in B. Similarly, if E intersection B is 5, from the same result we can have E is equal to E intersection A union with 5, means E is equal to E intersection A. Again, the intersection of two sets is one of the sets, means the same set is the smaller set, which means E is a subset of A. So that means either A is completely contained in B or E is completely contained in A. What was required to be proved here. So we have proved all the theorems today. Dear students, we'll continue with the further next theorems, and if you have any problems regarding these theorems or